Okay, so these are the section 2.4 notes, and this is the library of functions and piecewise functions. So there's two main parts to these notes. Number one, you're going to get the parent functions for just a ton of graphs. Theoretically speaking, you've learned how to graph all of these before, maybe not in a ton of detail, but you've learned the basics of them. And we're going to start talking about transformations. So we're going to learn about how to transform any of these graphs. You've done transformations, you did them in Algebra 2. You spent most of your time working on transformations with quadratics and absolute value functions. We're going to build on that this year, and we're going to add in a ton of functions. And we're going to see how we can graph all of these functions off basic transformation rules. This is going to be super helpful for us because when we get into logarithmic and exponential functions and trigonometric functions, all of them are going to abide by the same transformation rules. So the earlier we can solidify our skills with transformations, the better off we're going to be in the future when we start graphing these other functions. When I go over these functions, I'm going to give you a ton of details on these functions. The entire purpose of these notes is to just kind of get a basic idea of a function if it hasn't been transformed. The most basic of a function. So none of these are going to have any coefficients. None of these are going to have any movement whatsoever. When I talk about the parent function, I am talking about the general characteristics of the graph. Now, when we transform the graph, a lot of these characteristics are going to carry over, and we're just going to make minor changes. But knowing your basic information about your parent functions is a huge help. So what I have here is we're going to start off, again, the following slides contain all the parent functions, and they're kind of annoying, and the book kind of assumes that we know how to graph these already. And I really want to highlight this word table of values. No matter what, every operation that you're about to see you can do. If you're struggling with graphing things, you can always plug things into a table of values, and you can use that table of values. That's a go-to that you can always do. You can start plugging in numbers and getting y values out. So that's something that you should never be afraid of doing. Okay, so the first thing that we have is a constant function, and that's saying that f of x is equal to c. Remember, any time that we have f of x, it's the same thing as y. And we're saying y is equal to c. And if we have y is equal to c, it's just going across there. Like it's going across as a horizontal line. So here it looks like c is 1/2, but what we're saying is c can be any constant value. So if y is equal to a number, or f of x is equal to just one specific number, you have this horizontal line across. Now your domain for these functions is all real numbers. And we can see that with the arrows on both ends of our horizontal line here. It goes on forever and ever in both directions. My range for these functions is literally the exact same thing as the function itself. Is y is equal to whatever value c. And I'm going to put number in parentheses because you might understand number a little bit better than c. But I'm just saying y is equal to that specific number. Domain, all real numbers. Your y-intercept here is going to be c, so that's your y-intercept. And in this case, you have no x-intercepts. Unless f of x is equal to 0. And if you have f of x is equal to 0, that's saying that you've got a horizontal line like this right across the x-axis, and then technically speaking, you've got an infinite number of x-intercepts because every part of this graph is touching the x-axis, and that's kind of less than useful anyway. So that's what a constant function is. That's kind of all the properties of constant functions, and you're only going to have one transformation of this, and that's changing the number. The identity function is also just a linear function. Its parent equation is f of x is equal to x. Its y-intercept is 0, 0. Its x-intercept is 0, 0. And its domain and range are both all real numbers. You guys have seen this before. You have been working with this since Algebra 1, when I taught quite a few of you. So you know what a linear function looks like. And to be honest, you've been doing transformations of functions since Algebra 1. Yes, we make it a lot more clear in Algebra 2 what a transformation is, but when you're graphing linear functions, when you're graphing a y-intercept with a slope, all that is a stretch factor and a vertical shift. and you didn't even realize it because we never put it in those words. So you've been graphing vertical stretches and vertical shifts for 3 or 4 years now. Last year when you did it with a quadratic and an absolute value function, it got a little bit different. It kind of changed how you see it, but you've been doing these transformations. And again, this is the idea that y is equal to x, or f of x is equal to x is the identity function. We don't have any slope, we don't have any y-intercept, we just have one equation here. I could go through and give you a table of values as well. Your basic table of values that you would use here when you're doing your transformations. If you have a x of -2, your y is -2. X of -1, your y is -1. 0, 0, 1, 1, 2, 2. They match up. And that's everything you need to know about a linear function at its most basic form. A quadratic function, also sometimes called a square function, we kind of tend to refer to quadratics in my class. Everything here, I stole a really good graphic on the internet here. Your domain is -infinity to infinity, or all real numbers. Your range is from 0 to infinity, or y is greater than or equal to 0. When you transform this, we're going to see how ranges here have a half that doesn't exist, and that's because it goes back up. We can look at this graph here. We can see that it touches the x-axis and it goes back up. So all of my negative y values aren't included in f of x is equal to x squared, or y is equal to x squared. You've got a y-intercept of 0, 0, and you've got an x-intercept of 0, 0. And again, obviously these will change with transformations, and you're going to have some different functions here. And then we have a basic table of values to go along with this as well. If x is -2, y is +4. If x is -1, y is +1. And this is all the information you need. Again, I realize I'm just kind of talking through this, but these are some basic things that we should, theoretically speaking, already know coming into class, and we're going to build on this more in coming weeks, but we need to start getting used to what these functions are. A cubic function, you probably haven't seen this as much. So one thing I should note, when we get to quadratic functions, we do have a shape for these quadratic functions. We don't call them u's, we call them parabolas. Please do not say parabola. Parabola is not the word. It is a parabola. All right, so then we have a cubic function. Again, I stole this graphic off the internet. I've literally never heard anyone call a cubic function a squiggle until I stole this graphic. Some people call it a squiggle. Apparently it's a math teacher thing since I've been Googling how to teach this lesson. Some people call this a squiggle, some people just call it a cubic function. It is what it is. A cubic function, its parent equation is f of x is equal to x cubed. Here, again, you're going to have a domain of all real numbers and a range of all real numbers. When you have those arrows going in both directions, you're going to have that domain and range in both directions. Your x and y-intercept are both 0, 0. You can see that it crosses the x-axis and the y-axis at the origin. And so we've got x and y-intercept at 0, 0. And we've got our table of values, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. Again, just kind of flying through information here, giving you everything you need to know about these functions, because when we start transforming them, you're going to use all this information in your transformations. All right, square root function. Square root function is represented as f of x is equal to the square root of x, or y is equal to the square root of x. This one, again, we've already kind of gone over our domain rules. Since your domain, anything that you take the square root of has to be positive. That means that your domain is only positive values of x. So x has to be greater than or equal to 0. And conversely, our range on this function is going to be y is greater than or equal to 0. Technically speaking, some of you might be asking, but I thought when you took the square root, you could get a positive or negative. In this term, we are only looking at the positive. If you had a positive negative square root that you were taking, you would end up with negative y's as well, and you would have a graph that looks like this, and this is not a function. So that's a no-go. Whenever you see something f of x is equal to the square root of something, you automatically assume that it is just the positive square root unless a negative is written out front. So in this case, when you're graphing them as functions, they are just assumed to be positive. The only time that you give a positive and negative result for a square root is if you're solving for something that has been squared. Your x and y intercept here as well are both 0, 0. That is a very common theme of parent functions. And we've got our table of values. You can notice here the table of values is a little bit different with your x's. The other ones, your table of values gave you x's always like -2 to +2. The square root changes. Again, since the square root can give you irrational decimals, you want to work with square roots. So basically this is this graphic and me telling you, when you start doing your transformations, when you start looking for values to plug in values that give you like x is equal to 0. You want to get 0, 1, 4, 9, 16 under the radical because those are perfect squares. Those are numbers we can work with. All right, the cube root function. I'm 99% sure you haven't seen this. Rarely have you come across cube roots at all in class. The cube root function is kind of the inverse. Well, it is the inverse of a cubic function. We'll learn more about inverses in February. So we've got a squiggle here. It's kind of a horizontal squiggle as opposed to a vertical squiggle. We've got our parent function, y is equal to the cube root of x. Also, we can call that f of x is equal to the cube root of x. Our domain is -infinity to infinity, which is all real numbers. Our range is -infinity to infinity, which is all real numbers. Gives you a good table of values. Again, we can see that our x's are a little bit different than those first ones because we're plugging in values that give us cube roots. -8 is a perfect cube of -2. -1 is a perfect cube of -1. 0 is a perfect cube of 0, etc. So again, this is just giving you information. And then finally, your x and y intercept here are both 0, 0. All right, your reciprocal function, we're also going to start referring to this in terms of a rational function come December. Your basics for this are your function is y is equal to 1 over x, or f of x is equal to 1 over x. You're going to have asymptotes at... you're going to have a vertical asymptote at x is equal to 0, and you're going to have a horizontal asymptote at y is equal to 0. Here, your domain is going to be all values of x, where x cannot be equal to 0. Your range is going to be all values of y, where y cannot equal 0. You've got no x or y intercept on this parent function. But every other number can be included. You're never going to cross the x or y axis because of those asymptotes. We will learn more about asymptotes come December. We're going to kind of cover them a little bit in the transformation notes just because we're going to need to know them for transformations, but we really kind of dig deep into rational functions in December. So if you're kind of confused with what's going on with the transformations, that's going to be okay because we'll go into greater detail on these in December. I personally am not a big graph your rational functions via transformations person. I'm a much more graph your rational functions via graphing rational functions person, but we still want to practice these transformations anyway. Table of values here is not that pretty. This one, if we have our x and y, -2 would be -1/2. -1 would be -1. 0 does not exist. 1 would be 1. +2 would be 1/2. I'm just turning these into fractions. So that's the basic table of values which we can work on here. And we are going to learn a lot more about this. We can see that it's kind of got this, this hyperbola shape. Something new. We're going to definitely dig in more though. All right, absolute value function. You guys are super familiar with these. These are your v-shaped functions. You got your table of values, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. You know that this means that f of x is equal to the absolute value of x. You can also write it out as y is equal to the absolute value of x. Here, your domain is all real numbers. Your range is all real numbers. And your x and y intercept are both 0. Finally, the last thing, the greatest integer function, we are not going to work with this a ton. We are not going to even really be doing transformations with this. This is something that you do start looking at in calculus, so the book does make a point of making sure that you're aware that you've seen it, you're aware that it exists, you have an idea of how it works. How a greatest integer function work, you can work this one of two ways. It can either look the way it looks on this, or it can look the other way where you've got the open circles on one end and the closed circles on the other end. It's kind of a weird function. Basically what this means is that, like, okay, anything from like x of 0 to x is equal to 1 falls as y is equal to 1. So like if x is 0.5, y is equal to 1. If x is 0.7, y is equal to 1. If x is 2.9, y is equal to 2. I'm rounding down. If x is equal to 100.5, y is equal to 100. If x is equal to negative 8.7, y is equal to negative 9, because we have to remember that we're going the other direction. If x is equal to negative 6.7, y is equal to negative 7. We're kind of doing this round down as a function. So it's represented by f of x is equal to bracket around x. And we kind of have that rule. You have this table here. The table doesn't do the world's greatest job of explaining all those decimal rules. That's why it's important that you take those notes on those decimal rules. If you miss them, make sure that you go back in the video, rewind, and write those down. The graph description is stair steps. Writing the domain for this is kind of weird. So I'm just going to write out the domain. Domain is every value of x so it's all real numbers. The domain actually is straightforward. Sorry, the range is what's weird. The range is all integer values of y. So you can see here that your y values only exist on like the literal y value. So here, like we've got a y of only 0, y of only 1, y of only 2, y of only 3. So you kind of have these y values that only exist as these whole integers. And then finally, the last thing, your x and y intercept are both 0, 0. I really don't want you to fret over this graph. This is literally just me introducing this to you. You're going to have a couple homework problems on it. I'm going to tell you right away, there's going to be no quiz or test problems on the greatest integer function. This is just to give you your first exposure. So next year, when you're in AP Calc and they start going over it, you can sit there and go like, oh yeah, I saw this in a couple sets of notes Mr. Yehlen gave me, and we looked at it 3 or 4 times. I'm not totally unfamiliar with what this is. All right, finally, last thing, piecewise functions. I have not fully done the piecewise function because, again, Google Slides does not let me make a bracket. Any piecewise function would appear as a bracket like this. Piecewise functions historically give students a lot of trouble because, again, we struggle with figuring out how to write things in terms of our domains, in terms of our x values. It's something that you just have to pay attention to, and you got to work on the little skills. All right, so the first thing that I'm being told is that my function starts at -1, and this is where x is -1. I don't care about my y's, I care about my x's right now. And what it tells me is my function is going to be -x plus 1 from -1, and this should just be a less than sign. Don't ask me why I did not catch that. And between x is greater than or equal to -1 and x is less than +1. So here what I'm going to do is I'm going to know, okay, my graph is going to start here at this x value. I don't know what my function looks like there yet. I'm going to go ahead and I know that x plus 1 is going to fall on the y-axis somewhere. So it's going to fall on the y-axis at its y-intercept of positive 1. Negative x, that means I would go up 1 and backwards 1, and this is at negative 1. So I stop here. My function does not go any more left because my first point is at negative 1. I do this until I get to 1, but it is just a less than at positive 1. At positive 1, I leave an open circle. These other are solid circles with a line between them because my function definitely exists at these points. So between the x values of negative 1 and 1, all my x values exist except for 1, where it's just a placeholder. That's me saying the function approaches this positive 1 and stops here. This is just part of my function because I've got another part of my function. The other part of my function tells me that my line is 2 at x is equal to 1. And it's not going to be a line here, it's just going to be a point. So y is 2 when x is positive 1, and I put a closed circle here because that's the value that exists at positive 1. The last thing I have is that x squared starts existing at x is greater than 1. X squared at 1 is equal to 1. You can go up to your quadratic function. You can scroll up in your notes and look at that table of values for your quadratic function and see that when x is 1, y is 1 for your parent function of f of x is equal to x squared. From here, I can start representing the rest of my quadratic function, 2, 4, 3, 9, and then I can draw my quadratic function. So I've got an open circle at 1. Piecewise functions are confusing, one, because you really have to pay attention to your greater than or equal to or just greater than signs. Greater than or equal to represent closed circles. Just having a greater than or less than sign represents an open circle. It is just something that you have to know. And you have to be willing to get it done. Graphing piecewise functions with domain restrictions, I've seen a lot of students do it. You've seen how your calculator does not do domain restrictions well. It causes more headaches. Knowing how to graph a piecewise function by hand is 30 times more important than knowing how to graph it on your calculator with a domain restriction. You have to pay attention to your equal signs, and you have to pay attention to the starting and stopping point of your function. If you know how to read your graph from left to right with x's, if you know what these terms mean, this is a pretty straightforward concept. A piecewise function just means you're breaking it up and kind of making a function out of different parts. It's like if you've ever heard the colloquialism piecemeal, where I'm going to make this dinner piecemeal. It's like you're taking random parts that you're really not sure and you're throwing it together to make one. Same thing with a piecewise function. You're making a function out of piecemeal. You're just taking little segments of other functions and putting them together and saying, cool, I now have a function that goes from -1 to infinity in terms of my x. I've got a function with a range of y is equal to 0 onwards. And again, I've got a few questions here. So the domain of the previous piecewise function, it started at -1 and then it goes on to infinity. You could also report this as all values of x where x is greater than or equal to -1. Both of these are acceptable. You only need to choose one of them. Find the values of f of 0, f of 1, and f of 2. So this is saying when x is 0, when x is 1, and when x is 2, what are your y values? Well, we already know 0 is easy because at 0, I've got a y value of +1. That was my y-intercept here. So f of 0 is equal to 1. F of 1 is the most complicated one here because I've got 3 things existing at f of 1. But it's told directly to me right away in my function. If x is equal to 1, y has to be equal to 2. There's only one value. And if I go back and look at my graph at x is equal to 1, I can see those 2 open circles. It's not equal to the open circles. It's only equal to that closed circle. So at my closed circle of 2, that is my y value when x is equal to 1. And then finally, f is equal to 2. That one's straightforward as well because we have part of that function up here. When f is equal to 2, or when x is equal to 2, f of 2 is equal to +4. Find the range of the function here. It starts at y is equal to 0, and then every single y value is represented. We can see that between our first function and that quadratic function, every y value from 0 onwards represented. but it's an open circle at 0, so that means I would use a parenthesis. So it goes from 0 to infinity, or all values of y, where y is greater than 0. That's another way that we can write this. So that's a lot of information. I realize piecewise functions are confusing. Please ask me questions on any of this. I want to make sure you get this. Piecewise functions do make up part of AP Calculus exams. They tend to ask questions on it because having the domain restrictions, it really kind of brings together a lot of idea of mathematics all into one form. I'm giving you a second example of piecewise functions because I think it's so important. This one is going to be like a total function. So first thing I have is the function 3x plus 2 if x is less than -1. First thing I'm going to do is I'm going to graph this function kind of like normal, or I'm going to figure out what my points are. This is the y-intercept, but this y-intercept's not going to apply. It's going to start at -1, but I now have my slope. It's up 3 over 1, but I want to work backwards here. So I'm going to go down 3 over 1, down 3 over 1, down 3 over 1, down 3 over 1. I'm going to erase my y-intercept. I just use that for a graphing reference. Now that I'm here, I see that it is just less than. X is less than -1, so that means that this x value of -1 has to be an open circle for this function. I will draw a line through my points, and I will put an arrow at the end to represent this goes on forever and ever. Next one's really straightforward. Y is equal to 4 from -1 to 4. And it starts at -1, and it goes all the way to 4, and both of these are closed circles because we can see the greater than or equal to for both of these. So I have a constant function that goes across these 2 points from -1 to 4, closed circles because they're both or equal to, and then I just use that function in terms of my x. The last thing I have is 2x minus 1 if x is greater than +4. Again, how I'm going to graph this, I'm going to graph this kind of like what the function would be. I'm just going to put light dots. You have your x-intercept of -1. You've got a slope of 2, so you go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And this is actually where your graph is going to start. So I'm going to erase all those other points. I just use that to get to my starting point. This is an open circle here because I've got the closed circle down here, and I still have to abide by the vertical line test. I still have to make sure that each x value only gives me one output. Now from here I can graph this function as normal. I only have one more point, and I will graph it, and it goes on forever and ever. This graph would have a domain of all real numbers. The range on this graph would be really funky. So your domain here is all real numbers. We have everything included. Your range would be from -infinity until -1, because it stops right here at -1, union, and it would be a parenthesis because that's an open circle, it's not a closed circle. In brackets, you would just put 4, union. It starts again at +7 and goes on to infinity. I would not have you write something out like that on a quiz and test. This is mostly for your own information and reference, so you can kind of see how I have to only talk about the y values that exist in order to list its range. Its domain is still all real numbers though, because every x value is accounted for. It's a really weird looking graph. It's hard to figure out your domain and range there. You have to be really careful. You have to pay a lot of attention. And I'm not going to say that it's hard. I'm going to say that it's tricky. There's a lot of things that can trip you up. There's a lot of details you have to pay attention to. Please ask me questions if you're confused on these piecewise functions. It's something that students historically struggle with, but with just a little bit of practice and making sure that you're asking questions when you're confused, you can master it way quicker than if you just settle for being good enough. You have a homework assignment tonight. Again, please reach out with any questions or concerns. Don't worry too much about the first half. If that first half seemed confusing, it is just an information dump. It is giving you as much information as I can possibly think of on all these parent functions. Piecewise functions, if you're confused on that, please reach out to me as soon as possible. It's important that we nail these down as quickly as we can. Thank you and have a great night.